So today we are going to the P block elements. We've already looked at the S block element, which is our group 1 and group 2. So today we are starting the P block element. And for the P block element, we are going to look at group 14 and group 17. So for the P block elements, they are also the main group elements because the main group elements are the S block and the P block. But for the P block, these are the groups from group 13 to 18 in the periodic table. The S block elements are the groups 1 and group 2. And for the electronic configuration, we have the valence electron in the p orbital, just like in the S element, we have their valence electron in the s orbital. For the p block element, we have their valence electron in the p orbital. And for group 13, we have just one valence electron. Group 14, we have 2. We have, for group 15, we have 3. So all down to 6 electrons in their valence shell, and that is for your group 18. And for your group 15, we have the half-filled stability. Likewise, for your group 18, we have the completely filled stability. So this is actually your periodic table. As I said, we have your S block and your P block are the main group elements. Then we have the transition elements, which are your 3D, your 4D, your 5D. Then we have the F block, the lanthanide and the actinide. So we've already looked at the S block, which is group 1 and group 2. So today we are looking at P block. And as I told you, we are looking at the group 14 and group 17. And after that, we are going to look at the D block elements. And I think we'll look at radiochemistry. Now, what are some of these distinctive features of your P block element? Just as we looked at some of the distinctive features of your S block element. As we said, they are all metals, they form ionic compounds and all that. Now for your P block elements, their chemistry does not actually follow a particular trend, just like unlike the S block element, where you have all of them as metals. So because they are all metals, so they have the same characteristics and all that. For your P block element, it doesn't follow that way because there's usually a change in character as we go down the group. So you are changing from non-metal to metalloid and to metals. Like your group 14, we have carbon, silicon, germanium, tin, and lead. Your carbon is a non-metal. Your silicon and germanium are metalloids, while your tin and lead are metals. Sorry. When we get to group 15 also, your nitrogen and phosphorus are non-metal. Your arsenic and antimony are metalloids, while your bismuth is a metal. You get to group 16, the same thing. It's only in group 17 that they are all non-metals. So you see that your P block element, they don't actually follow the same. Their chemistry is not the same. So there is difference in chemistry of all the members of the group. And as I said, this actually distinguishes itself as we go down, where you have non-metal, metalloid, and metals. So there's usually a change in character from non-metal to metal as we go down the group. Also, there's usually different oxidation states. Unlike your S block element, your group 1, they all exhibit +1 oxidation state. Group 2, they all exhibit +2 oxidation state. But for your P block element in the same group, most times does not exhibit the same oxidation state. So they exhibit more than one stable oxidation state. Who is that? The person wants me to remove him or her from this class, Abby. So for the oxidation state, they usually differ by 2 units. What do I mean by that? If you look at group 14, they usually have oxidation state of +2 and +4. So they differ in steps of 2 units. For your group 15, you normally have oxidation state of -3, +3, +5. So there's a difference of 2. For group 16, you also have +2. You have -2, +2, +4, +6. For group 17, you have -1, +1. You have +3, +5, +7. So you see that they differ in units of 2. And this is usually due to what we call the inert pair effect. The inert pair effect, what do we actually mean by the inert pair effect? It's actually the tendency of the outermost orbitals, which is the s orbital, to remain unshared in their transition element. That is, it's usually due to the presence of d orbitals as we go down the group. These elements have d orbital in between them. So most of them exhibit, so as you go down the group, you have elements having the d electron. And because of this, the outermost electron, which most times is the s orbital, they don't want to share that their valence electron. And so that is actually what we mean by inert pair effect. That s orbital remain unshared. And that is why most times as you go down, you see that the elements are more stable in +2 oxidation state. So that is actually what we mean by inert pair effect. So the lower oxidation state becomes more stable as group is descended. So that is why I said most times the s orbital, they don't want to share their electron. So they will remain. So the s orbital remains. For the p orbital, as you descend the group, stability of the covalent bond decreases. So they form stronger covalent bond, but the stability of the covalent bond decreases as we go down the group. Also, the first element in each of the group cannot expand its octet. And we see this in group 14. So because of this, the maximum coordination number for your group 14 is 4. But as we go down the group, of the d electron, because most of the acycloid and to metal, and most of the metals, most of them are transition elements. So they have d orbital. So because of the presence of the d orbital, they can expand their octet. But the elements higher, especially the first element, they can't expand their octet because of absence of d orbital. So your p block element, another good characteristic or distinctive feature is that they exhibit allotropy. What is allotropy? The existence of different crystalline or molecular forms of the same element in same physical state, which we don't see in S block element. We don't see allotropy there. So for your carbon, you have diamond and graphite. For your sulfur, you have your rhombic and monoclinic. For your tin, you have your white and gray tin. So these are some of the allotropic forms of your group of your P block elements. Now we look at the trend. What is the trend in these group elements? So we see that the trend is not smooth, unlike the S block element, because of what? Insertion of the transition metals between the S and the P block element. So we have that, you have the S orbital group 1 and group 2. We have the P orbitals from 3 to 18. And in between this S and P block element, we have the transition metals. And this transition metal, most of them run across to P block element. So we say because of the insertion of transition metals between the S and the P block element. So what are some of these typical properties? One, we have anomalous first row element. This anomalous first row element is also found in your S block element because of the small size and the high charge or high electronegativity of the first element in each group. So that is an anomalous behavior. We saw that in lithium. We also saw that in beryllium. So it's typical for most first elements. Then we have the second row element, which shows less electronegativity than first row element. Of course, as we go down, the electronegativity decreases. But when we now get to the third row element, we now have even a higher electronegativity. And this is due to the transition element coming between the S and the P block element. Because we know that for the transition element, they usually have a higher electronegativity. They have high ionization energy because of increase in nuclear charge, and there's no screening effect. So that is, who is that? Who is that disturbing my class? So that is why the third row element has higher electronegativity. So we call it the middle row anomaly because of the presence of the transition element. So there's a So there's a gradual decrease in electronegativity for the last two elements. The last two elements are usually metals. Like for your group 14, the last two elements are your tin and lead. For your group 15, the last element is your bismuth. For your group 16, we have your polonium, they are all metals. So there's a gradual decrease in electronegativity for the last two elements. And the last element has higher electronegativity than expected. Why? Because of the lanthanide contraction. The lanthanides actually have increased nuclear charge, no screening, so the electronegativity is usually high. That is actually what we call lanthanide contraction, because there's a high decrease in ionic radius, as I said, due to poor screening effect because of the 4F electrons. So there's more nuclear charge, or there's more nuclear pull. And when you have more nuclear pull, then we expect the atoms to be smaller. And when they are smaller, then we have higher electronegativity. So those are the distinctive few features of your group 14 element. So we'll look at the group 14 elements proper. As I said, for our group 14 element, we have our carbon, silicon, germanium, tin, and lead. As we said, your carbon is a non-metal, your silicon and germanium are your metalloid, while your tin and your lead are the metals. And these are the symbols. Please note the symbols. And the melting point decreases down the group. We can see that carbon has the highest melting point because your carbon has the highest nuclear charge. It's very close to the nucleus. So the nuclear pool is very high, because as we go down the group, what happens is that nuclear pool decreases, there's more shielding. So your carbon has the highest melting and boiling point. And the melting and boiling point decreases as we go down the group, because the forces holding this element together as we go down, because of increase in size, decreases. So the force of attraction reduces. But when we look at tin and lead, we see that there's an abnormality here. We expect tin to be higher than lead, but we expect lead, of course, we expect tin to be higher than lead, but now lead is higher than tin. Why? Because your tin, the structure of your tin is distorted. The structure of your tin is distorted. That is why you see that your tin is having a lower melting point than lead. But naturally, the melting point decreases down the group. Electronegativity also decreases down the group because of decrease in nuclear charge or nuclear pull. There is increase in shielding effect. and there is a reduction in ionic radius. So your ionic radius, actually there's an increase in ionic radius. And this is the electronic configuration. You see that they all have their valence electron, which is 2, is in the p orbital. But as we go down, you see that we have the d electrons coming in as we go down the group. So this is actually what affects the inert pair effect. And the oxidation state for your group 40 element is usually +2 and +4, but they are more stable in the +4 oxidation. The higher ones are more stable in the +4 oxidation state. They are all stable in the +4 oxidation state, but you see that your lead, is more stable in +2 than +4, but the others are more stable in +4 oxidation state. And as I said, we can explain this using the inert pair effect, because the electrons will be preferred to, once they lose more electron in the s orbit on the p orbital than the s orbital. The s orbital does not want to share its electron. It doesn't want to lose its electron. So that is why you have this in oxidation state of +2, while the others are +4. So we look at the structure and bonding. So for structure and bonding, we have your carbon has a giant molecular structure. Carbon, silicon, and germanium has your giant molecular structure. So that the structures they are large when you say giant. And the bonding is covalent for the 3 of them. But for your tin and lead, these ones are metallic. So they are metallic, and we have the white tin and the gray tin. This is the allotropies. While for your carbon, we have your diamond and graphite. So for carbon, as I said, the allotropic forms are your diamond and the graphite. For your diamond is hard. It's harder than your graphite. And this is due to the bond, which is sp3 hybridized. When we get to our graphite, we see that our graphite is sp2 hybridized. So this is your CH. This is your carbon, hydrogen, 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 hydrogen. So you have your carbon being connected to another 4 carbon, which is CH4. So each carbon is sp3 hybridized. So each carbon is bonded to 4 other carbons. So you have, if this is your carbon, you have 1, 2, 3, 4. And because of this, it has a very high, the melting point of your diamond is high. And this is actually why you have.
I can't ready for 2 weeks now.
Who is Amina Toma? Who is Amina Toma? Can you shut yourself before I remove you from this class? Will you shut yourself or before I remove you from this class? Amina Toma. So it's actually because of the diamond. That is why you see that carbon has a very high melting point, because of the allotropy of your carbon, which is actually diamond. So your diamond has a very high melting point because of this covalent bond. So it's extremely hard. It does not conduct electricity. It's chemically inert. Unlike your graphite, which we are going to see, that has sp2 hybridized. And because the way the structure is a layer structure. Your graphite is so you know when you layer something, there's a space. It goes in layer. So that is why we have these free electrons. And because we have this, what we call the localized electrons, because they are free, so they can actually conduct electricity. So that is why your graphite can conduct electricity, because of this, the way it is layered. It has a layered structure with the localized electrons. So there's electrons are flowing free here. and your graphite is brittle, is soft. When you say something is brittle, it is not smooth. So it's brittle and it is soft. And because it has this layer structure and with the localized electron, that is why it can conduct electricity. So the conduction of electricity is actually along these layers. So we look at the allotropy of tin. We've looked at the allotropy of carbon, which is your diamond and your graphite. You should be able to know the difference between the two, why one can conduct electricity and the other cannot conduct electricity. So for your tin, we have the white tin and the gray tin. For your tin, the difference actually lies in the temperature. When your tin is cold, when it's cold, it is actually the gray tin. But at high temperature, when it's heated, it goes to the white tin. Why is Obinna raising his or her hands up?
No.
Yes?
Question now.
Eh?
I have a question.
I'm still teaching. When I'm done with my teaching, you can now ask your question. Okay? Thank you. Okay. So when I'm done teaching, we'll ask questions. So that is your white and your gray tin. So your gray tin when it's cold and your white tin when it's hot. So your gray tin is non-metallic. That is when it's cold, it's non-metal. But your white tin is metallic. So those are the two difference because of their texture, or what to call the nature. So now we look at their reactions. We look at their reactions. So the first is chlorides. So they form chlorides. Of course, formation of chloride is reaction of the metal with halogens. So we are looking at the chlorides we are actually looking at is actually the chloride. So your group 14 element form two series of chlorides. The dichloride and the tetrachloride, that is oxidation state of +2 and +4. But as we move down the group, what happens is that the stability of +4 oxidation state decreases. I've already told you the why it decreases because of the inert pair effects. In inert pair effect, we saw this in your lead, where your lead exhibits more of +2 oxidation state than +4. So your carbon forms more stable tetrachloride. Your carbon is higher up, so your carbon is more stable in +4 oxidation state, so it forms more tetrachloride. So we have a carbon tetrachloride and all that. So the stability of +2 oxidation state increases than the group. I've already explained this and the reason. So all the elements form tetrachloride, that is +4 oxidation state. And these are their tetrachloride, their carbon tetrachloride, the silicon, the germanium, the tin, and the lead tetrachloride. And they are all simple covalent compounds because the difference in electronegativity between the elements is not much. Sorry, unlike your metals, where they form more ionic compounds because of the difference in electronegativity. But for this one, the difference in electronegativity is not much. So they usually form covalent molecules, and their shape is usually tetrahedral. Because it's 4, their shape is tetrahedral, and they usually exist as liquids at room temperature, not as solids. But one thing we should know is that the molecule as a whole is non-polar, but the bond is polar. So the molecule as a whole, when they form this molecule, is non-polar. But the metal chloride bond is polar. The metal chloride bond is polar due to the difference in electronegativity. But the molecule as a whole is non-polar. But each element with their chloride, is the metal chloride bond, is polar due to the difference in electronegativity. So for boiling point, We've already said that it decreases from carbon to silicon. Thereafter, a steady decrease is observed. Your lead chloride decomposes even at room temperature. So what it means is that it's not your stability of your tetrachloride decreases as we go down the group, because the boiling point decreases from carbon to silicon. So as we go down, the boiling and melting point decreases. And that is why your lead will decrease even at room temperature. Unlike your carbon decomposes under a very high temperature. And the compounds hydrolyze in water. They hydrolyze in water to form, most times they form acidic solutions. But carbon does not undergo the reaction due to its inability to expand its octet. So their hydrolysis in water is because they can expand their octet. That is why they hydrolyze in water. So that is why we said that carbon does not undergo hydrolysis because it cannot expand its octet. So we look at the mechanism of hydrolysis. This is your silicon tetrachloride in water. So this is actually electron rich, electron deficient. This is the metal, of course, it's electron deficient. So there is actually a donation. So this is actually what we call our nucleophile. This is our electrophile. There's a donation from the nucleophile to the electrophile. And this gives you this unstable compound. So the hydrogen actually abstracts your chlorine to form your HCl. So what happens is that this scenario continues over and over again until all the chlorine has been fully replaced. So that is actually the mechanism of hydrolysis of your tetrachloride in water. So as I said, they usually lead to the formation of an acid. So your silicon tetrachloride hydrolysis in water will lead to the silicic acid, your silicic acid. So that is for the chloride. So we'll now look at the oxide. They also form two types of oxide. We have the monoxide and we have the dioxide, +2 and +4. And the stability of the monoxide increases down the group. And the monoxide are more basic than the dioxide. The dioxide are more acidic, like your carbon dioxide. Of course, our carbon dioxide is acidic. So that is, we say the monoxides are more basic than the dioxide. So the dioxide are more acidic. So these are your dioxides. So all the group 14 elements form the dioxides, oxidation state of +4. Your carbon dioxide exists as a gas at room temperature and pressure. Your CO2 is a gas at room temperature and pressure, but the others exist as solids. So because they exist as solid, of course, they will have a higher melting and boiling point than your CO2, which is a gas. And they have giant covalent or giant ionic structure. So like your tin and your lead will have giant ionic structure because they are more, your tin and your lead, because they are metals, they will be more ionic. So there is decrease in stability because as you can see that these are, the dioxides are +4. So there is decrease in stability of the dioxide as we go down the group, and there's also a decrease in basicity. So this is actually the structure. Sorry. So this is the structure of your group 14 compound. So this is your silicon. This is just example how they occur. This is your silicon dioxide. So this right here is your silicon, and this is your oxygen. This is your oxygen. So what is showing that you have the element or the metal, and we have the oxygen attached. So this, in terms of silicon oxide, that is the structure. So you have your silicon, and we have your oxygen, and we have your oxygen. So the red represent the silicon, while the blue represent the oxygen. So what is the summary of the properties of the oxide? We said our CO2 is acidic. Of course, your monoxide are more basic, so the dioxide are more acidic. So your CO2 is acidic, which is a non-metallic oxide. When it is, as we said, it dissolves in water to give weak acidic solution. But most times, we said carbon does not undergo the reaction due to its inability to expand its octet. That is the tetrachloride. Please don't get it wrong. That is the tetrachloride. So your carbon dioxide can dissolve in water to form a acidic solution. Your silicon dioxide is insoluble in water. Your silicon dioxide tends to be more amphoteric. So that is why it's insoluble in water, but it can dissolve in alkaline. So your silicon oxide is acidic, sorry. Your silicon, I know your silicon is a metalloid. Your silicon is a metalloid, sorry, it's not amphoteric. So your silicon oxide is acidic. And that is why it's insoluble in water, but dissolves in alkaline solution. So because it's acidic, then it can dissolve in a base. So because it's acidic, it can dissolve in a base. That is why they say it dissolves in conc alkaline solution. Your silicon oxide is acidic, but your silicon is a metalloid. And when we say something is a metalloid, that means it's a semiconductor. When we say something is a metalloid, it's a semiconductor. Your germanium and your tin, their oxides are amphoteric. Mind you, I told you your germanium is a metalloid. Your germanium, a metal, is a metalloid. Your tin is a metal. But their oxides are amphoteric. So your germanium oxide, your tin oxide, and your lead oxide, they are all amphoteric. And because they're amphoteric, what it means is that they can dissolve both in acid and in a base. Your CO2, the oxide, is acidic, so it can dissolve in water. Your silicon oxide is acidic, so it can dissolve in alkaline. Please note these differences. Your germanium oxide, your tin, and your lead, they are amphoteric, so they can dissolve in both acid and water, and in both acid and base, but they will not dissolve in water. That is one characteristic of elements or compounds that are amphoteric. Now, they are hydrides. They all form hydrides, and the kind of hydrides they form is a tetrahydrides. Tetrahydrite, of course, we expect that because of their more stable in +4 oxidation state. So your carbon, their tetrahydride is actually alkanes. That is your CH4. Hydride is reaction between the element and hydrogen. So your carbon, the tetrahydride of your carbon is your alkane, CH4. Your silicon is your silane. Your germanium is your germane. Your tin is your stannane, while your lead is your plumbane. And your plumbane is unstable. It's more stable in +2 oxidation state. You see that your lead is usually more stable in +2 oxidation state. So that is why even your plumbane is unstable, but it's stable in +2 oxidation state, which we saw because of the inert pair effect. All the lower hydrides are colorless. gases. The liquids have low boiling point due to weak intermolecular attraction, and reactivity increases as we go down the group. We've already looked at why reactivity increases as we go down the group when we looked at group 1 and group 2. So we look at carbon. You know, carbon is special among this group. Aside being the smallest element, has the highest electronegativity, has the highest melting and boiling point. Your carbon cannot expand this octet. By now, you understand what I mean, because it does not have the d orbital. So the maximum bond it can form is 4. And again, your carbon can catenate. Carbon is the only element among your group 14 element that can catenate. That means it can form chain with itself. So you can have your carbon-carbon chains. Your silicon catenate, but you see that your silicon is not silicon-silicon. It's usually silicon-oxygen chain. It's only carbon that can form, that can catenate with its element. And it's only also carbon that can form pi bonds. Because for your carbon, you know we have your carbon-carbon, carbon double bond, carbon triple bond, carbon oxygen. Each of them can form 1 sigma bond and 1 pi bond. It's only your carbon triple bond that can form 2 pi bonds and 1 sigma bond. So carbon is the only member of this group that can form a pi bond. And the carbon forms gaseous oxide. Their carbon monoxide and their carbon dioxide are gaseous, unlike the other oxides that are solid. The other oxides are solid, but the oxide of your carbon are gaseous. Now we look at the greenhouse effect. When we talk about the greenhouse effect, we are talking about the warming effect of your CO2 and water vapor on the earth. That is the greenhouse effect. And this effect occurs when the gases in the lower atmosphere, when they absorb IR radiation from the earth, and they now give it back to the earth. But now, it's a normal phenomenon, it's a natural phenomenon. But because the level of this CO2 and the water vapor in the atmosphere increases. And why do they increase in the atmosphere? This is due to what we call deforestation, falling down of trees, which is supposed to take up this CO2. We are now falling them off. And there's also too much combustion of fossil fuel. And there's too much, oh my God, who is this? Who is disturbing this class? So as I said, the warming effect of your CO2 and your water vapor in the atmosphere is a natural phenomenon. But what happens is that when there's an increase in your CO2 and your water vapor, due to what? Deforestation, that is falling down of trees, because these trees are meant to take up this CO2 in making photosynthesis. So you fall down these trees, there's combustion of these fossil fuels, there's use of so much CFCs, the chlorofluorocarbons. So there's also increase in your methane due to combustion of fossil fuels and all that. So all this leads to increase in your CO2. So as this leads to increase in CO2, what happens? Instead of the natural phenomenon of just natural warming, so the warming effect is like increased. So when the warming effect increases because of all these activities, what happens is that there is actually what we call melting of ice caps. The ice caps are already there, but because there's now an increase in temperature because of our activities, the ice caps are now melting more. And when they are melting more, what happens is that there's more flooding. So that is why you see that when it the rains are so heavy, we now have has increased because of the what we call global warming. It's actually the global warming that is melting the ice. These ice are supposed to be there, but they are not melting. Of course, when they melt, they turn to water. So we now have more water. So This has led to melting of ice caps and flooding of low-lying countries. So, of course, countries that are low, that are very low, or even people that are living in lowland areas get more of this flooding than people that are living in high rising areas. So that is actually what we mean by the greenhouse effect. As I said, the presence of the CO2 and water vapor is a natural phenomenon. It's supposed to just do what it's supposed to do, the natural warming. But because there's an increase in your CO2 because of all these activities, it leads to melting of the ice. So the temperature is increased more than expected. And when this happens, there's melting of ice. And the melting of ice, of course, leads to more flooding to the low-lying countries or people living in low-lying areas. Any question? So we can ask our questions.
Okay, ma. Good morning,
Thank
ma.
you. Morning, Obina, how are you?
Fine, thank you, ma.
Okay.
My question is, when you talk about the allotropes of carbon, you only emphasize on diamond and graphite.
Yes. You know, we have fullerenes. Have you heard of fullerenes?
Yes, ma. That is
Carbon
650.
Thank you, carbon 60. Yes, because these are the
Yes,
ones, these are the more common ones that we know. We have soot. We have other allotropes of, do you understand? But these are the two common allotropy of carbon. It's not that it's not only the only. I did not say only. Did I put only? No. Has two important. These are the two important ones. Your diamond and your graphite. We have our fullerene, carbon 60. We have our soot. We have our coke. There are so many, isn't it?
Yes, ma. Yes,
Okay,
ma.
thank you.
Okay, ma. The second question is, when you're talking about their oxides,
okay,
you said their dioxide are basic, while their monoxide is basic. Does it mean that CO, when it reacts with water, it's going to form a basic oxide?
Where are we? Let me bring it.
The oxide, ma.
Yes, I want to get this slide.
Okay, ma.
This is. Can't even. It's under the oxides, okay? The monoxides, the dioxides, the monoxides are more. The monoxides are more basic. The monoxides are more.
I'm listening, ma.
The monoxides are more basic than the dioxides. Your CO2, when you dissolve it in water, it forms acidic solution. But your monoxide, when you dissolve your monoxide in water, yes, they can form acid, but they will be less acidic than your dioxides. Do you understand what I mean? That's when you say the monoxide, we did not say they are basic. We said they are more basic than the dioxides.
Okay. More basic than.
So they are more basic. Not that they are acidic, but your dioxides are more acidic. So if your dioxides are more acidic, then your monoxides will be more basic. Am I right?
Yes, yes.
Uh-huh.
Thank you.
Okay,
Thank you.
Thank you. So any other question?
Hello.
Okay, dear.
You said oscillation states other than group oscillation states generally differ in steps of 2 units due to inert pair effects. Then give a definition for inert pair effects.
Okay.
So I didn't get the definition. You said.
Okay, when we talk about inert pair effect, you normally see it in your P block element, because as we go down the P block element, you see that you have transition elements in down the group. Unlike the group 1 element, they are all metals. There's no transition element, isn't it? And the transition element, you see that you have your d orbitals. They have d orbitals. So what happens is that the inert pair effect will only be observed for your p block element because of the presence of this element that we have the electrons. Now, what happens is that because they have this d electron, sometimes you can see the s and the p orbital coming in between the d orbitals. It's not always okay. But what happens is that as you go down the group, you see that there's a tendency of the elements losing electrons more from their p orbital. They have both the s and the p, like your cis s and your cis p. But the elements prefer to lose, the ones that lose electron from the p orbital, they don't lose electron from the s orbital. So that they don't want that s orbital, they don't want to share the s orbital. So because of that, as you go down, most times they have oxidation state of +2 because of that 6s or 5s electron. So they can give out or share from their p orbital, but they don't from the s orbital. So the tendency of the outermost atomic s orbital, which is your either your 6s or your 5s, to remain unshared, especially in the transition element. That is why you see that those elements we prefer to exhibit oxidation state of +2, while the others are exhibiting oxidation state of +4. Let me show. You see, as we go down, we are having the S. You now see that you are getting the D electronic configuration. So you now have 5D10, you have 6S, you have 6P. So for this element, once they share from their 5P orbital, you see this 6S, they will not share, and they will not give, they will not share. So that is why they would prefer to, so your lead will be more stable in +2 oxidation state than +4 oxidation state. So this is what we call the inert pair effect, is because of this presence of this d orbital. It's only common with transition elements that find themselves in between the p block elements.
Thank you.
Okay, dear. So any other question? Any other question?
Sorry, ma. I wanted to know if group 3 was discussed.
No. We discussed group 1, group 2 for the S block element. Then we are discussing group 14. Then we discuss group 17. We are not discussing group 13, group 15, and group 16. That would be too much now. What is your exam? Is it not just 100 questions? Abi, how many, Seth? Huh?
Thank you, ma.
Okay.
Thank you, ma.
You want us to discuss everything? And when are we going to finish?
No, ma. No, ma.
No, ma. Thank you.
So, in the absence of any other question, our time is already spent. So I'm going to put up the lecture on the LMS and the slide. So, Dr. Fashional student, on Monday, you go back to your group with Dr. Fashional. My student, on Monday, by 9 we'll meet, but it's still likely we are going to shift the class. Do you understand? Because of my lecture 9 to 11. But I will log in and we'll discuss about that. Okay, so have a nice weekend. Bye-bye.
Thank you, ma. Same to you, ma.
Thank you, ma.
Thank you very much, ma.
Thank you, ma. Bye-bye.
Bye.
Thank you, ma. Bye-bye.